Hello, everybody. My name is Raj. I am in the SimCenter test support team. So when products are released into the market, it is expected that they would last for their designed lifetime. So to avoid any unwanted failures due to the repeated use of the products, companies they make these products go through some rigorous fatigue or durability testing. This testing could take a lot of time, this fatigue or durability testing. So the objective of this webinar is to show some techniques on how to accelerate this fatigue testing. We'll be looking at various methods, looking at their pros and cons. We'll be looking at a unique way to handle that, how to accelerate the test. So with that, this is the agenda for this webinar. First, we'll be going through some fundamentals about fatigue, including concepts like minor rule and rainflow matrix. Then we'll be looking at accelerated fatigue life testing, and then we'll finally wrap up with some final comments. So with that, first let's take a look into the fatigue fundamentals. Fatigue life refers to the gradual degradation and the eventual failure of a product due to the cyclical loading that it experiences. When there is repeated cyclical loading on a product, it can lead to failure, and that's what is fatigue. Now the emphasis here is on the cyclical loading rather than just a static loading. Static loading means a one-time loading that can be there and it doesn't change over time. It's just one time. However, the cyclical loading, it changes. And what has been found out is that the fatigue life due to this cyclical loading, the amplitudes required for this fatigue can be much smaller than the static load that is required for the failure of the material. But due to the repeated nature or the cyclical nature of this loading, that's what causes this failure. So the fatigue life of a component can be influenced by various factors like the loads it experiences, the geometry or the shape of a component, and its material properties, which can include what type of material it is made from, and also other things like the process which was manufactured, like the surface finish and things like that. The loads, they can be in the form of stress applied on the component or strain or even accelerations. So all these come under the category of loads. And these are the loads experienced by the product during its operation or the normal usage. I also use this term called damage, which is a measure of the fatigue. And we will see later that when this damage equal to 1, that is when the failure occurs. One of the influencing factors for the fatigue life is the material and its properties. So to determine the material properties due to the cyclical loading, typically a testing is performed called coupon testing. So shown here is such a testing machine. In this testing machine, like a coupon, like a test specimen is put in there, and then it is subjected to some cyclical loading, which has some pattern like this. And you can see the x-axis is time and this y-axis is stress. And this loading can be in the form of axial loading, or it can be like bending loading or torsional loading. Different types of loading can be provided in this testing machines. From this testing, we develop what is called as SN curve, a stress and number of cycles, SN curve. And a result of that is shown here. So in this case, the x-axis is number of cycles and this y-axis is stress. And this typically has a shape like this. It has an exponential decay shape where as we increase the stress levels, the number of cycles to failure that reduces. As the stress levels are increased, the number of cycles to failure that is reduced. So if when the stress is about 100, this number of cycles to failure is about 1000. And then when the stress level is about 1000, the number of cycles to failure is about 200. So they are inversely related, the S and N. Now this is a nonlinear shape. If we put them in a log scale, x-axis is in the log and the y-axis is in log, this curve shows up like a straight line here. And this is what is commonly the stress and the number of cycles that is shown. And I say stress, but it can be generalized in terms of the load to be looked in terms of acceleration or even strain. You can do that. So this is the shape. It has a gradual downward slope because the number of cycles to failure increases as the stress is decreased. So this SN curve, it represents the material properties of the component we are testing. There are other factors which influence the fatigue life, like the load and geometry. We're going to be looking at the loads in the next few slides. As I said earlier, this SN curve, this represents the number of cycles to failure. N represents the number of cycles to failure. So for a particular stress level, the number of cycles to failure is shown by this SN curve for that material. So for different types of material, this SN curve will be very different. For aluminum, it will be different, and for iron or steel, it will be very different. And the slope of this curve, which is related to a factor called K, that changes with different materials that are tested. And even for the same material, like there will be high carbon steel and low carbon steel, and for even them, this SN curve will change. So it's important to know the material it is made of. Some of the standard properties for standard materials for commonly used metals like aluminum, steel, it is already known. But if the composition is different based on how much amount of carbon is there or any other material, or if you have a composite, you need to have the specific SN curve for that material. If we look at further details about the SN curve, we'll see that this is the same shape that I was showing earlier, which was this line here, this downward slope, and then we'll commonly see that this has a shape like this. It starts from this point due to cyclical loading, and then there is a slope part, and then there is a flat region. The flat region here, that means that when the stress levels are less than this, that means that it can last for infinite life. And so that is called as the endurance limit. That is the stress below which the material will have infinite life. And then there is a region called as the elastic region. And in this region, there is a slope for this line, and that area is commonly called the high cycle fatigue region. When the failure happens between more than 10,000 cycles but less than 1 million cycles, that is called as a high cycle fatigue in this elastic region. And then there is this area when the stress level goes beyond more than this yield strength, that is when it goes into the plastic region, and that is where it can have low cycle fatigue. It is important to know that these infinite life, high cycle fatigue, and low cycle fatigue, there are different regions for them, and the mode of failure can be very different in these different areas. For example, if you look at the high cycle fatigue, you can see a small notch or a small crack occurring, and that is a failure. So this is high cycle fatigue, and this happens in the elastic region. However, for low cycle fatigue, it can be plastic failure, which can mean that the damage is irreversible and the shape of the damage is very different, and it's failure occurring in this example from both sides, not just one side. So the failure modes can be different in the high cycle fatigue versus the low cycle fatigue. So this is how this endurance limit, yield strength, and ultimate strength, they relate to static test. That is shown in this picture here. For different materials, this endurance limit and the ultimate tensile strength, they are different. And you can see steel commonly used, it is 690 megapascal. For copper, it is only about 97 megapascal. A measure of the fatigue is the damage. A way to measure that damage is from the cyclical loading by using what is called Miner's rule. Miner's rule gives us a measure for the damage that occurs in a component based on the number of cycles and the stress level it experiences. So for example, if you see here, if there is a cyclical loading pattern like this, 2 cycles as shown by this gray curve, and then 2 cycles in this blue curve. Blue has the higher amplitude and the gray has the lower amplitude. What Miner's rule says is that you can compute the total damage from these 2 cycles at this level of stress in this gray by referring to the SN curve and finding what are the total number of cycles for failure for that. So there are 2 cycles experienced in this gray amplitude. From the SN curve, it may be known that it requires 6 cycles for failure at that stress level. And so the damage caused by these 2 cycles is 2 divided by 6, and that is equal to 1/3, 0.33. For these 2 at a higher amplitude at this blue level, from the SN curve, we know that the number of cycles for failure is 4, and the component actually experienced 2 cycles in that. So that will mean the damage caused by these 2 cycles is 2/4, and that is equal to 0.5. And the total damage from these total 4 cycles is computed as a summation, as just a linear summation, and that is equal to 0.83. The damage can be expressed simply using this mathematical formulation, the example for which is shown here in the bottom right hand side. So Ni refers to the number of cycles at a given amplitude, and the uppercase N represents the total number of cycles for failure at that amplitude based on the SN curve. Okay, so the Minor's rule is a good way to know what is the total damage accumulated due to the cyclical loading. When the damage is equal to 1, that is when a failure occurs. Now the failure can mean a component being fully broken or a small crack can happen. Either of these are examples of damage. We see that here in this idealized case, it looks like a pure sine wave and termination of the cycle is very straightforward. But most commonly in real life situations, we'll see that the load pattern is something which looks like this, a more complicated waveform. In this case, it becomes very important to know what is actually a cycle. Is the small wigglings that happen here, is that a cycle? Or is it large fluctuation? Is that a cycle? To know what constitutes a cycle, there is a method for that, which is called rainflow counting method. The rainflow counting method can be broken down into these steps. One is called hysteresis filtering. Very small fluctuations can be ignored, and how small is too small, that you can determine actually by controlling parameter, and you can specify that. And then once you do the hysteresis filtering, then you go to this peak value filtering, which is when there is a change in the direction of the load. When it's going up, it is not counted as one cycle, but when it goes up and then comes down, that's what it is looking for. Then it goes to a process of discretization, where the whole y-axis is classified into bins, like as shown here. And then you can use a 4-point counting method, where if the inner points are bound by the exterior points, that counts as a cycle. If you think of this whole time history that you have and then classified into these bins, and then you look for points where the inner points are within the outer points, and those actually constitute a cycle. It's important to know from which load to which load you are going, and from that you populate this table, which shows from the load level and to load level. Here, if we see, if we are going from level 8 to level 7, and so if we look at that, then from load level 8, it is going to 7 to load level, and so it happened once, so that counts as 1. And similarly, this yellow point, it is going from 4 to 3, and so that counts as 1 cycle. This whole entire load history, or the time history of that trace, is broken down into this matrix, and in this matrix, in this axis is from and this axis is to, and the number corresponds to the number of cycles experienced from that level to that level. Commonly, it is shown in a picture like this, from and to, and you will see the color here represents the number of times the event has occurred. So if there is red color, that means this from and to combination has occurred more number of times than, let's say, a blue or pink. This is a way to count the number of cycles from that. And from this number of cycles, then we can use the Minor's rule to calculate the damage from this load history based on this rainflow counting method. So first we go through this rainflow counting, then go through the Minor's rule to calculate the damage from the cycle, and then sum them all up to come up with the cumulative damage from this entire load history. So that is the information, that is the foundation that we will use for this accelerated fatigue life testing. Typically, when we go through this fatigue life testing, the whole process involves multiple steps. So first you have to do a test plan preparation, where you want to know where you want to measure the loads on the component and what type of loads are they going to be, whether to do instrumentation in terms of sensors that you will use, like a strain gauges or load cells or accelerometers. You do the instrumentation, then put your product through its normal usage. In the case of automotive, there are proving grounds on which these cars are driven, and then you collect the data from those proving grounds. And these proving grounds can have different types of road surfaces, like smooth roads or concrete roads or Belgian blocks. All these types of different load conditions, they're all tested in this. You collect the data from this proving ground, and then you analyze the data and then come up with a profile, a load profile that you want to use for laboratory testing. You want to give that input load to your shaker so that you can represent the proving ground loading conditions on this shaker. That is an important consideration, because you cannot do all your testing on the proving ground, because if you want to complete certain number of cycles like, or a certain lifetime, like 10,000 hours. Like if you want to do that on this proving ground, that requires a lot of manpower, and then you require a lot of time on the proving ground. So that is why take the measurements from the proving ground and then use that information to give input to your shaker and do the testing in the lab, where you can run the test 24/7 in a controlled way, and then you can run even unmonitored. Like, there doesn't need to be a driver or somebody to notice that. You can just go through the process of setting the test, and then it can be set up to run for a long time. This is the typical durability testing or fatigue testing process. Measure the loads on the proving ground, then you want to give that as input to your shaker, and that can be electrodynamic shaker or a hydraulic shaker, and it can be different multi-axial shaker or a single axis shaker. And there are different types of shakers available, and depending on your need, you will want to use a particular type of shaker. So once you have this fatigue testing data, then you want to apply this process of accelerated fatigue life testing so that you can do the testing faster. Even after you have collected the loads from the proving grounds or from the real life operation of the vehicle, like driving on the common highways or on other road surfaces in the case of automotive, to go through the process of testing for that long using that time history can take a lot of time. So you want to come up with a way how to accelerate that test so that you can do the test in a less amount of time. And there are different methods that are available for accelerating the fatigue life testing, and those include increase the load level. Suppose you measure certain load levels and then you just increase the load level. You can do that because we saw that as we increase the load level, the number of cycles to failure is less. So maybe that makes sense. And the other concept can be apply the cycles faster. If you do this taking a certain period of time, and then within the same period of time, perhaps you can make it faster and apply more number of cycles. Remember, from S-N curve, if we apply number of cycles for failure, we want to apply more number of cycles for failure within the short period of time. So if you do it faster, perhaps that may help, and we'll take a look at that. And the third concept is omit low damaging events from the test profile. That is an important concept, and that is where we'll focus for the rest of the presentation. Now, these methods for this accelerated fatigue life testing, they are time domain methods. There are certain frequency domain methods. We are not going to cover that today in this webinar, but we already have a seminar on that. So I've included the link for that. You can please check that out. So first concept, accelerated fatigue life, to increase the load level. We saw from the S-N curve, it has a certain slope. If let's say if the slope is 5, increasing the load by just 15% reduces the testing time by 50%, 50. So a small change in load could lead to significant decrease in the number of cycles for failure. That is an important observation. Rather than testing at the measured load levels from the proving ground, if we increase the load levels by about 15%, then that will just reduce the testing time by half. So that sounds very promising. How does it work? Let's take a look at that in our TestLab Neo software. Let me show you my TestLab screen. So this is in TestLab Neo, where I want to show if we bring in some data that was measured from a strain gauge, and I can then and I want to increase the load levels and to see how that changes the number of cycles for failure. So if here I have some data, I have this strain data, and I'm going to put that into my input basket. Okay, there it is. I can look at the channel. So this is how it looks. In the display, we can see x-axis is time and this axis is strain. And this actually was measured from a strain gauge, from a rosette. We can see the strain goes from 900 to -500. We want to scale this, and we want to see how much difference does it make in terms of the number of cycles for failure. We go to this processing, and I'm going to load the process that I have previously created for this, and that I call is stress life scale, and I'm going to put that here. I'm going to use this data from this input basket. So here I'm applying this scaling factor of 1.15, and I'm going to put it through the rain flow counting, and then I'm setting stress life to convert from strain to stress using some material, sample steel material, and I'm going to use minus rule for calculating the damage. and then I have the result which are stored in this active analysis portion. So with that, I can see what I got. So even though it may not be very clear here, I'm showing the original time history. The red one is the original time history, and the blue one is the scale with the scaling factor of 1.115. And if I look at some statistics, like the life statistics, using these material properties, it calculated this design point blocks, which shows if you repeat the same time history to how many number of times this block have to repeat it for the failure. So with the original trace, it said you have to repeat that about 5,000 times for that failure. And for the scaled one, which is with the amplified 15% increase in loading, it says that it requires 2,500 blocks. So you can see that it reduced from 5,000 to 2,500. So that is the 50% reduction in the cycles or the time for testing. That's what I'm talking about. So a 15% increase in load for this material produced 50% reduction in the cycle for failure. So you can see how you can easily determine that based on the measured time history and using this rainflow calculation and this stress life method. That can very easily be done in our software called TestLab Neo. Now it gives a couple of other interesting things. If I look at the rainflow, I'm put the limits to 3, okay. So I can maximize here. So in the rainflow, this is the, or I'll put the limits to optimized. Because it's only a scale curve, here it went from the original, which was the maximum was about 472, it went to 543, or actually we saw about 900, and then it went to 1052. That is the 15% amplification factor. The shape looks exactly the same because we didn't remove any data from there, so that makes sense. And similarly, we can look at the life curve. And let me deactivate the legend. So here, what we see is based on the material property, this is the shape of the curve, and it's showing the histogram of the original loads and the number of cycles. And then this is with the increased loads and the number of cycles. And we can see from here, for this maximum load, this is the point corresponding for the life curve. Now, this material property curve that represents a constant level of amplitude, and it represents the number of cycles for failure. But based on this loading that we have, the amplitude levels are not always the same. So the life curve will be something which is parallel to this, and it will show points and the relationship between the stress level and the cycles for failure. So for this particular load history that we have provided, this is showing the stress. And so when we increased from this stress, we increased by a factor of 1.15. So that is what it is saying. That is the point at which it will present the corresponding number of cycles for failure. Here there is a certain number of cycles, and then as we increase the load by 15%, the number of cycles reduce significantly as shown here. And if you continue to increase the load, maybe you can go up till here. It still has a linear shape to it. So that is a good information to know. If we go back to the slides, so that is summarized here, the time history and the rainflow and these points which corresponds to the design point, like the increased load and such. So we can increase the load, but if we increase the load significantly, what could happen is that in this case, if you have current test levels is here, and if you increase the load levels to some point here, the mode of failure in here is the elastic region failure, but the mode of failure here is the plastic region failure. The mode of failure can become very different if you increase the levels too much. So we want to accelerate the test, but if you want to increase the load level too much, then it could cause unrepresentative failures. So in the field, from the market or in the proving ground, you may see a failure like this where a small crack has developed, but if you increase the level too much, it can go into the plastic region failure, and that failure mode can be very different from this high cycle fatigue failure. So it may not be representative of the actual failure mode that we see on the field. We shouldn't just increase the load level arbitrarily. When increasing the load level, we should take into consideration that we should not go out of the material region for that. In our example, when we saw in the software, we saw that going from blue to green, we were still in the elastic region. So that is a good thing. But you have to be careful not to go into the plastic region or some other failure mode region. And that is the downside of this increased load level. You can go into a failure mode which is not representative of what you are trying to capture. The other method that is used is called the applying the cycles faster. So here you see an example of that. I have this original time history which is about 14 seconds long, but I just reduced it to about 7 seconds. So by compressing the time history, and which is shown by this green curve. And what you will see is that when we do that, the spectrum, input spectrum, if you look at that, it can be very different going from this red to this green curve. And what could happen is that if you have a natural frequency, which is somewhere around here, let's say, somewhere in this region, because you have changed the frequency profile, you will now be exciting a mode which was not being excited previously with the original time history. So you have to be careful when applying the cycles faster. You shouldn't be exciting something that you don't want to excite because it was not being excited by the original time history. When you apply cycles faster, it can also lead to changes in temperature, and now that can also be a big deal because that can induce some other failure mode also. So you have to be careful with this method. With both these methods, increase the load level and apply cycles faster, there are some downsides to it in terms of what you can do. There is a more optimal method, which is a way to omit low damaging events. We saw from the rainflow matrix, we'll have from and to diagram. And in this rainflow matrix, the points close to the diagonal, they are actually low damaging because the change from and to is from within short amplitudes. That doesn't cause much damage. The points which are further away from the diagonals, those are the ones which cause the high damage, as indicated by this red box here. Points in the green box, they don't cause that much damage. Perhaps a better way to accelerate the test is actually to remove these points which don't cause much damage. So we will be left with these points which cause the high damage, and that may just be the way to go about accelerating the test. Consider this also. This same information, if you look at the x-axis, this is cumulated damage, and here is the amplitude, the load. And so we can see that 99.5% of the damage, cumulative damage that you can see, is actually caused by the loads above 4,000 and not the ones below 4,000. If we look in terms of cycle count versus the amplitude, for this 4,000, that is only 70 cycles out of the total 10,000 cycles. These 70 cycles which have the amplitude above 4,000, those are the ones which are causing 99.5% of the damage. So to accelerate the test, we can remove all these cycles which are not causing much damage and which have these low amplitudes. To accelerate the test, if we just remove these low damage events, then we can speed things up. This is actually implemented in our test lab Neo software. One of the methods we have is called time compression method. And so let's take a look at that as an example. So I'm going to accept the results from this, and I'm going to create a new section, and I'm going to call it demo 2. I'm going to remove this existing process that I had, delete this, and I'm going to load a new time history for this. And this time I'm going to load acceleration. I want to show that we can get an idea for the loading based on acceleration data also. So acceleration, and then I'm going to put this in the input basket. If I go here, then I can look at the time history. So it is about 45 seconds long. You can see different events, and the y-axis is acceleration in terms of G's. I'm going to use this omit low damage cycle. There is a built-in process for that included as part of the standard test lab install. So I'm going to open that. And that process, you can find it damage-based time compression. So that is included within our standard test lab software. So I'm just going to load this data, and then use that for processing. I just loaded the data and then loaded the process. I'm going to run it. I didn't make any changes to the process. I just loaded it by itself without making any changes. We'll take a look at the parameters from that. But first, let's take a look at the results. So active analysis, I can look at this time history. So the original time history is there, which is shown by this red curve. And then there is a compressed time history. It removed the low damaging events based on the criteria that was included, and it came up with this new time history, which is only about 10 seconds lag. So it was about 45 seconds that got reduced. Now notice the amplitudes. The maximum amplitude is about the same as the one which we saw in the original time history, and the maximum and minimum still say the same. That is the beauty of this method, that you are not introducing unwanted behavior because of the increased loads. You're keeping the load levels the same and accelerating the test. If you look at the load spectrum, this is how it compares. The red one is the original and the black one is with the compressed time history. You can see that the frequencies, they are staying about the same. The amplitudes, they're slightly increased because we are doing less number of averages, and that is to be expected. But more importantly, if there are any big peaks in the frequencies, they are not being shifted, which was one of the downsides of make cycles faster method. Now, if we look at some statistics that come from this result, it is showing the results here. So it is saying that originally there is 100% damage. Now here, one important point is that what we measured was acceleration in G's, but the SN curve refers to stress and number of cycles. So there is no easy way, I guess, to convert from acceleration to stress, but we do what is called a pseudo damage calculation. So from that, it is saying if the original time history, it caused 100% damage, with this compressed time history, we got 94% damage, which is pretty good. It is using only 23% of the total time. So original time history was about 45 seconds and got reduced to about 10. There it is saying now it is only 23% of the time. So we have accelerated the test by about 5 times without changing the load level, without shifting in frequencies, and causing about 94% of the original damage. So that is the beauty of this method. It compresses the time history without compromising on the failure mode, so to speak. So you can see how easy it was to set up and bring in the load data and then apply this process here. The main method in this case, let me maximize that so that we can take a look at that clearly, is that damage-based time compression. This is an algorithm which is based on the rainflow counting. We specify a level below which we want to remove the data, not above, but below which we want to remove the data, because that is low damage cycles. And then we go through this process of calculating some statistics and rainflow. Everything is included as part of the standardized method. Even if you bring in train data or stress data, I can do the similar calculations and make use of it. This damage-based time compression method, here I'm saying that I'm targeting about 80% of the damage to be retained, and what I actually got was much higher. Let me accept this one. And again, I want to do this calculation, and let's say if I want to go with retaining only 60% of the damage. And there are other options available. You can specify in terms of the maximum range and such. When we remove some time blocks because they are low damaging events, we need the way to combine the different times to compress them. It uses good techniques for that, using a fading technique so that there are no abrupt changes in the time history. And that is important because abrupt changes in the time history or discontinuities can excite broad range of frequencies, which is undesirable. So if we make this about 60%, and I can run this again. So if I say this damage to be retained, I have reduced it from 80% to 60%. If we look at active analysis, I can take a look here. It reduced the time history further. If it reduces the time history further, now if we look at the statistics, what we'll see is that now we are getting only damage of 75% compared to the original 100%. Now we are 75%, and when we had written the damage to be 80%, it was giving us 94%. The total length of time, it got compressed significantly. Now it is only 11% of the original. So you can play with this parameter. See, sometimes compressing it way too much will not be desirable because the material can become hot. You have to be careful that you are not introducing any other failure mode because of that. So you can see how easy it is to do this type of calculation in our TestLab Neo software. We looked at the spectrum and the time history, but if you look at number of cycles, you can see that it's not very obvious here, but it got reduced by a factor of about 5 with the 80% retention. So you can do this type of accelerated fatigue life testing using this compressed time history. You can use this profile to give it to your shaker. You can get the same amount of damage with the compressed time history. So that is the accelerated fatigue life testing. With that, we'll come to the final portion of this webinar. We'll do a wrap up. So we looked at the various method for this accelerated fatigue life testing with the increased load level and the applying cycles faster. But we found that omitting the low damage events, that may be the best way to go about doing this, because we are accelerating the testing without increasing the load level, because increasing the load level can cause unrepresentative failure going from elastic region to plastic region. And then also frequency of excitation is the same, so it's not exciting something beyond some other frequency range, which was the downside of the applying cycles faster method. How fast you want to accelerate, that is dependent on temperature. Part becomes too hot, then that is not desirable. A rule of thumb is generally you don't want the part to become too hot, maybe about 10 degrees or so. That should be good, 10 degree Fahrenheit. Or sometimes in many situations, if the testing is done in a lab, you can use a fan, cool it down. So with that, I come to the conclusion of this presentation.